Welcome to this NPTEL course on robotics, basic and advanced concepts. In the last lecture, we looked at control of constrained and parallel manipulators and also Cartesian control of serial manipulators. So in this lecture, we look at force control of manipulators and we will use these ideas of Cartesian control of serial manipulators that we developed last lecture. So let's continue. If the manipulator is moving in free space, we need to do position control. Basically, we need to track the desired trajectory. If the robot is assembling, grinding, and manufacturing, okay, so there is some contact with the environment, position control is not enough. Okay, so in all these three cases of assembly, grinding, and manufacturing, we need to apply desired force and or moment on the environment. Okay. So one possibility is that we apply force and moment with passive stiffness in the end effector. Okay. So most end effectors, or in fact for that matter most joints, will have some passive stiffness. Okay. So it is compliant in some sense. It is not completely rigid. So if you have such joints or with some stiffness, we plan a trajectory such that it is just inside the contacting surface. So think of it this way: we want to grind a surface. We make sure that the trajectory is just a little bit inside the contacting surface. Okay. As a result, when position control is being tried, it will try to reach to that point just below the surface, and as a result it will always be in contact with the surface. Okay, and it will also apply some force if you know how much is the stiffness which is at the end effector. This is not so easy to do, okay, for the following reason. Okay, the main problem is there is always some error in position control. Okay, and we cannot be exactly following the trajectory which is just inside the surface. So let's say a fraction of a millimeter inside the surface. Okay, so due to the error in position control, it is possible that the grinding tool is not touching the surface, or it is going too much inside the surface. So hence we have excessive interference. Okay, the other problem in this approach of using passive stiffness is that it is not possible to apply desired force to the environment. Okay, most of the time the environment stiffness is very high. There will be very small strains, and the displacement due to the passive stiffness for a very stiff environment is difficult to measure. And it is possible that the stiffness also changes, or the environment also changes. So a joint space control similar to constraint motion, or what we saw that the tip is tracing a curve in the workspace, is not suitable, as I had mentioned earlier. Okay, we have 6 degree of freedom manipulator. It is not so easy to convert that curve into joint variables because inverse kinematics may not be analytical. There are other reasons also which we had discussed. We can, however, use Cartesian control strategy very easily. Okay, and this can be extended to the control of force which the end effector is applying to the environment. So let's start with some very simple basic problem. We have this mass m which is in contact with this environment. The environmental stiffness is Ke. Okay, it is applying some force F to the environment. The displacement of this mass is x, and we also assumed, due to uncertainties, that there is a disturbance force which is acting on this mass. Okay, and we are looking at only one direction, force being applied in one direction, and control of that force in only one direction. Okay, so the applied force from an actuator is F of t. The disturbance force is F disturbance. The displacement of the mass is x of t. The environment stiffness is Ke, as I have mentioned. So hence, the force exerted by the environment is Ke into xt, like spring constant into the displacement. And the aim is to control Fe to a desired value, Fe desired, by applying F of t, this external force from an actuator. Okay, so the equation of motion of this system can be very simply written as F equals mx double dot plus kex plus some F disturbance. Okay, standard spring mass system with an external force. We know that ke times x is Fe. Okay, so we can rewrite this equation in terms of Fe. So we can write F is mke inverse Fe double dot plus Fe plus F disturbance. Okay, so this is very, very similar to a second order ODE which we discussed for a joint rotation for a single link robot. Okay, in this case, we have a single mass which is applying a force. In that single link manipulator, we had a torque acting at the joint and the joint was rotating. Okay, so we can use PD or PID control to make sure that this F which you are applying gives the desired Fe which we want. Okay. However, we are now very familiar with model-based control. Okay, we see that there are lots of advantages of model-based control schemes, and hence let's try and see if we can develop a model-based controller for this task of applying a desired force onto the environment. So just following the control law partitioning concept, we will say F is some alpha F prime plus beta. For the moment, let's assume alpha is mke inverse, beta is Fe plus F disturbance, and hence we will be left with F prime is equal to Fe double dot plus kb Ef dot plus kp Ef. So Ef is nothing but the error or the difference between the desired force and the measured force. So we must have some sensor which will measure the force also. So if you go back and substitute all this and simplify, we will get a second order force error equation. Okay, this is the closed loop force error equation. It is second order linear, okay, with constant coefficients. So Kp and Kv are the derivative and proportional gains, and we can set them to some value for required performance. Now there are some issues. Okay, first is we do not have any knowledge of F disturbance. So hence we cannot use it in the model based term. So remember, we have said beta is Fe plus F disturbance. But in principle, the whole idea of F disturbance is we do not know the disturbing force. So hence we cannot compute beta because this is Fe plus F disturbance. Okay. So if you set beta is equal to Fe desired, okay, not Fe plus F disturbance, we can see that the steady state error will be F disturbance by 1 plus mke inverse. It is not 0. However, it is small. Why? Because ke is typically very large. Okay, so ke of say a steel will be very, very large number, and this ke inverse will be m divided by some large number, so it is very small. So the error is of the order of F disturbance. So this is the best that we can do. The second issue is we can measure FED, but we cannot normally measure the rate of change of the force applied to the environment. Okay, so there is also no physical sense in the use of derivative of a desired force. So if FED dot and FED double dot cannot be specified, okay, then we might as well drop it. Likewise, Fe measured, but Fe dot is very, very difficult to measure. We can measure that force exerted by the environment by strain gauges or some sensor, but the rate of change of the force applied by the environment or applied to the environment is very impossible. But we can estimate Fe dot by Ke into x dot. So if you can measure how much is the velocity of that mass, which is x dot, okay, then knowing or getting an idea of Ke, we can find Fe dot. Okay, so hence dropping Fed dot, Fed double dot, and also beta as Fed and Fe dot as Ke into x dot. If you make all these substitutions, the control law now becomes F is equal to M KPF KE inverse EF minus KVF X dot plus FED. Okay, so you can see it is proportional to the error. Okay, it is derivative gain into X dot. So there is no FED dot. Okay, and there is a bias term FED. So this is the best that we can do if you are going to use a model based scheme to control the force which this mass is applying to the environment. Okay, so how do we choose KPF, KE and KVF? Okay, so before that, let's quickly go to the block diagram. We have this spring mass, single mass connected to a spring applying a force and also experiencing a disturbing force. So the input is F. We measure Fe and X dot. With X dot into KVF, we subtract. Okay, and then with Fe and FED, we find the error in the force. We multiply by KPF divided by KP, and then we subtract this KVF into X dot, and that multiplied by mass will give the force. And then we add this Fe desired directly to obtain the force. Okay, so this is the block diagram of a force control of a spring mass system. Okay, and if we have set the gains KPF and KVF properly, then this Fe desired will approach the whatever we want. Okay, the measured Fe, which is the force measured by the sensor, and Fe desired will go to 0. The difference between those two will go to 0. So as I said, it is difficult to estimate Ke as it can change with time. Okay, the stiffness, initially you are grinding a steel, then you can be grinding something else, aluminium. So the stiffness can change with time. So what is the basic idea? We can choose Ke large as most environments are stiff. So what is large? We have to choose a large number and then play around with it. We have to do some simulations to see what is happening. Terms in beta and the dropped derivatives of FED are not there. Okay, so some terms like F disturbance was dropped, FED dot and FED double dot were dropped. As a result, you can show that the error between the desired force and the measured force does not go to 0 as in a second order system. Okay, it becomes a small number. It is of the order of the disturbance force, but it is not 0. We can extend this idea to 6 degree of freedom manipulator. So in this case, F and X become 6 by 1 entities, remember, not vectors. So F becomes force and moment, which is acting at the end effector. M is the Cartesian mass matrix, and Ke is a 6 by 6 positive definite diagonal stiffness matrix. Okay, X contains XYZ and the orientation, a representation of orientation of the end effector. So these gain matrices KPF and KVF are 6 by 6 positive diagonal definite and diagonal matrices. Okay, so as I said, by choosing this KPF and KVF for each one of these axes, we can hope to ensure that we can apply the desired force. Okay, now let's continue. So when we are dealing with forces, okay, there is this very important notion or principle of duality. So what it says is we cannot control force and velocity in the same direction. Okay, why is that? Because if you say that, let's consider a simple mass, we know F equals ma. So if you say that the force is specified, the acceleration is automatically determined. I cannot choose arbitrary force and arbitrary acceleration. Okay, likewise, I cannot choose arbitrary torque and arbitrary rotation of the end effector. They are related, and in fact the force, torque and the linear and angular velocity are related through power or through Newton's law and Euler's equation. So for example, in robotic grinding, Force can be controlled normal to the surface, being ground, and the velocity can be controlled tangent to the surface, being ground. Okay, we cannot control the force in the tangent to the surface and velocity in the other direction. Okay, because it doesn't make sense. Okay, or we cannot control both the force and the velocity tangent to the surface. So this duality is analogous to partitioning of control torque in planar 2R robot while satisfying a constraint. Remember when we saw that the tip of the 2R robot was tracing a curve f of xy equal to 0. I showed you there was a tau phi which was tangent to the surface and a tau n which is normal to the surface. So these two are different. Okay, we cannot have both velocity in the normal direction and force in the normal direction. Only force in the normal direction and velocity in the tangent direction. Okay. So this Cartesian control scheme naturally extends for force control. So what do? In any robotic task, we divide into subtasks. First, in contact with the environment or in free space. Okay. So if the robot is moving and then goes and touches a surface, till it is moving in free space, it is moving in free space. Okay. And when it is in contact with the environment, we have to use a different kind of control scheme. So tasks in contact with the environment, position control and force control directions need to be found out. Okay, so if you are in contact with the environment, certain directions you can do position control, certain directions you can do force control. Okay, how about when it is in free space? In all directions or for all components x, y, z and orientation, we do position control. There is no force which is acting on the end effector. So to divide the task into position and force control directions, there was this notion of natural constraint and artificial constraints which were developed in the late 80s. Okay, you can see this book by Craig for details. So a natural constraint on position and orientation occurs when the manipulator is in contact with the surface. It involves variables that cannot be controlled. Okay. A manipulator cannot go through a surface. So the natural position constraint exists when it is in contact with the surface. A manipulator cannot apply arbitrary force tangent to the surface. Okay, so there is a natural force constraint in the tangent direction. So whenever it is in contact with the environment, we can find certain variables which are natural position constraints. Position means both x, y, z and orientation, and certain force constraints which are fx, fy, fz and moments mx, my, mz, which cannot be controlled. Okay. So if you think about it, the natural force position constraints are normal to the surface and the natural force constraints are tangent to the surface. Okay, so depending on what kind of task you are doing, we can generate the natural position and force constraints for any robotic tasks. Okay, whenever it is in contact with the environment, and I will show you some examples. On the other hand, there are some constraints which are called artificial constraints, and these are all position and force variables. Position means x, y, z and orientation. Force means fx, fy, fz and moments that can be controlled. Okay, so as an example, let's say that the manipulator is in contact with the environment. The position variables in the tangent direction can be controlled. So I can trace a path in the tangent directions. I can go faster or slower. I can choose a desired trajectory in the tangent direction of the position variables. I can also control the force in the normal direction. Okay, I can say apply 1 Newton force at all times in the normal direction. So this natural and artificial constraints partitions the position and force variables into two complementary sets. Okay, and what do these complementary sets really mean? Basically, they follow from the principle of duality. So if there is a force constraint in the normal direction, okay, there cannot be a position constraint in the normal direction. I can control the force in the normal direction, but not the position. Okay, this is again from the principle of duality. So next we show some examples. So for example, consider this grinding example, which we have been talking about all the time. So we have this grinding wheel, and there is a surface. This wheel is grinding a surface. So first thing to do is we need some coordinate system, okay, which in that coordinate system we will write all these position and force variables and say which ones can be controlled and which ones cannot be controlled. So typically we set a coordinate system Cx, Cy, Cz with this curly bracket C, which is the constraint coordinates. So now let's look at the 6 position variables, meaning Vx, Vy, Vz, omega x, omega y, omega z, and 6 force variables, which is Fx, Fy, Fz, Mx or Nx, Ny, Nz. Nx, Ny, Nz are the moments which are acting on this constraint coordinate system. So as you can see, this Vz, so in this example, z direction is normal to the surface, is along the normal. And x and y, x is along the grinding wheel in some sense, along the axis of the grinding wheel, and y is perpendicular to x and z. So as you can see, Vz is a natural constraint. Why? Because you cannot go into the surface or you cannot leave the surface, then it is no longer in contact. Okay. Likewise, Fx and Fy, the force variable along x and y direction, okay, cannot be controlled. Okay, and likewise Nz, which is the rotation about this z axis, these are natural constraints. So if you can think of some friction, okay, so there is a force, but the normal force and the friction force are related. We cannot have arbitrary friction force Fx and Fy. The variables which are subjected to artificial constraints, meaning the variables which can be controlled, are this Vx and Vy. So they are the variables in the tangent space at that contact point. Okay, so I can say that I want to go in the x direction with such and such velocity and such velocity in the y direction. So Vx and Vy can be controlled. Likewise, Fz can be controlled. I can say that we want to apply a certain force along the z direction. How about omega x and omega y? You can see that omega x cannot be controlled, because if you have some omega x, if you rotate about the x-axis, okay, then it will leave contact. Okay, similarly omega y. If I rotate about the y-axis, the grinding wheel will lose contact. Okay, so Vz, omega x, omega y, Fx, Fy, and z, these are the natural constraints. And the variables which are artificial constraints or variables which can be controlled are Vx, Vy, Fz, and think a little bit about it. It is also Nx, Ny, and omega z. Okay, so as you can see, these two are complementary. If there is a Vz here, there is a Fz here. Vz cannot and Fz cannot be in the same set. Fx and omega Vx cannot be in the same set because of the principle of duality. Let's take one more example, which is I have a crank, I have a wrench which is turning a crank. Okay, so again we set up a constraint frame, which is Cz, which is the vertical direction. Cx is along the direction of the crank, and Cy is the direction in which you are rotating. Okay, so the variables which are artificial constraints, meaning which can be controlled, are this velocity along the y direction, rotation speed about the z-axis, Fx, Fz, Nx, and Ny. Okay, so you can see that these two are different. Here we had Vx, Vy, omega z. Here we have Vy, omega z. There is no Vx here. Likewise, the variables which you cannot control are Vx. You cannot have a velocity in this direction. Then, you are sort of bumping against the rest of the body of the crank. Likewise, you cannot go up because then you will lose contact. Okay. and Fy and Mz, omega x, omega y, Fy and Mz are natural constraints. So for every robotic task such as grinding or turning a crank, and we will see later for an assembly operation, we can divide the 6 position variables and the 6 force variables into variables which can be controlled and which cannot be controlled. Okay, so this is the hard part. This needs, the programmer needs to think about it and partition these variables. But he has some tools to do it. Basically, we have to use this principle of duality and also what exactly is the task doing. Okay, we know in the normal direction forces can be controlled. In the tangential direction, positions can be controlled, and so on. So some ideas are there. We use those ideas to partition this 12 variables, 6 position and 6 force variables. Okay, so whatever I said is summarized here. So the manipulator is holding a grinding wheel on a surface. We define a constraint frame C. Cz is normal along the normal. Cx and Cy determine the tangent plate at the point of contact. For grinding, a desired force along the normal and a desired trajectory on the surface is required. Okay, so all constraints described in C using linear velocity components Vx, Vy, Vz, angular velocity components omega x, omega y, omega z, force components Fx, Fy, Fz, and Nx, Ny, and Z. Okay, so we cannot lose contact, okay, or interfere. So hence Vz is 0. Grinding wheel has area contact, so omega x, omega y equal to 0. Just a little bit more detail so as not to lose contact. Fx, Fy, and Z determined by friction and are not arbitrary. Okay, we cannot set whatever we want. Vx and Vy determine the desired trajectory, how we are moving this grinding wheel on the surface. So hence they are artificial constraint. We also need a desired force along the z direction, hence this is an artificial constraint. And likewise, omega z, nx, and ny from the principle of duality are artificial constraints. Okay, so we can partition all these 6 plus 6 variables, force and position variables, into something which cannot be controlled and something which can be controlled. In the robot turning a crank, again C is as shown in the figure. X-axis is along the direction of the crank, Y is the direction where you are rotating, and Z is the vertical direction. Okay, so again Vx, Vz must be 0, so no motion possible along X and Z. Okay, because otherwise it will interfere or lose contact. Omega x, omega y 0, so no rotation possible along Cx and Cy axis. We cannot apply any force along the y-axis or apply a moment about the z-axis. So the artificial constraints are Vy and omega z. Artificial force constraints are Fx, Fz, Nx, and Ny. Okay, so you can think about it and see that what is mentioned here looks sensible and looks correct. Let's look at one more task. This is a very important robotic task, which is basically assembly of 2 components. And here we are going to look at a very simplistic case of assembling a peg in a hole. Okay, so this is the peg, this is the hole on the surface, and we want to assemble this peg into this hole. Okay, moreover, as far as simplification is concerned, we'll assume it's a 2D task. Okay, so it is in the xz plane. The y is in the normal to this plane of this hole. So first case here, A is showing when the robot is moving this peg in 3D in space. Okay, so it is not in contact with the environment. So the constraint frame is x is along this direction, z is along the vertical direction. After a while, this peg comes in contact with the surface. Okay, this is the second kind of subtask which this peg in hole requires, that you come and touch the surface. Then you move along the surface such that the peg comes directly on top of the hole. You may not come directly on top of the hole at the first instant. So you have to move a little bit here and there. Then once it is directly on the top of the hole, you push it down. So the full peg in hole assembly is divided into moving in free space, touching the surface and moving on the surface, then finding the hole and moving into the hole, and then at the end of the motion, nothing is moving. Okay, it is all assembled. Okay, so this is a classic problem in robotic assembly of a peg in hole. So as I said, the assumption is 2D motion of the peg, no friction between peg and hole surface, and sensor is available to find the hole. Okay, as I said, you move along till you find the hole. There must be a sensor to find the hole. So as I said, it is divided into 4 stages. First is motion in free space, which is figure A. Motion while touching the surface, which is figure B. Stage 3 is insertion of the peg in the hole, figure C. And stage 4, completion of the assembly. Okay, so let's go back and see these pictures. So this is stage 1 in free space, stage 2 moving on the surface, stage 3 insertion into the hole, and stage 4 when everything is done, it is completed. Okay, so let's try and find the natural and artificial constraints for each one of these stages. So the first stage is very simple. Okay, what is the natural constraint and what is the artificial constraint? The artificial constraints are the position and XYZ and the orientation are completely controlled. Okay, so we have Vx, Vy, Vz, omega x, omega y, omega z. So Vx and these are 0, and we want to approach the plate along the z direction. So this is some desired z velocity. We also do not want to rotate this peg. So all the desired angular velocities or angular orientations are 0. So corresponding to this, fx, fy, fz, nx, ny, nz, these are natural constraints. Okay, the variables which cannot be controlled when it is moving in free space are nothing but the forces which are acting on the end effector. There are no forces which are acting on the end effector. Okay, so in stage 1, the manipulator is under pure position control. In stage 2, once the peg touches the surface, no motion along the z-axis or rotation about the x or y-axis is possible. Okay, so you cannot penetrate the surface or you cannot rotate at one place. Okay, so we also cannot apply force along the direction of sliding. We can control the position along the direction of sliding, but we cannot control the force. Okay, so Vz is 0, omega x is 0, omega y is 0, fx is 0, fy is 0, and nz is 0. Okay, these are the natural constraints. Okay, if you think about it, you cannot penetrate the solid, which is Vz, and so on, and fx and fy equal to 0. So what are the artificial constraints? We would like to apply a small force along the z-axis to ensure that it is always in contact. We control the velocity along the plane, along the x and y axis. So we have Vx is some v sliding velocity, Vy is 0, and Fz is Fc. And this Nx, Ny, omega z are 0. Okay, this follows from the principle of duality. So we would like to control the sliding velocity and the force along the z direction. In stage 3, the peg is going into the hole. Okay, so what are the natural constraints? Think about it. We see that Vx, Vy, omega x, omega y, Fz, and Nz are 0. Why is Nz 0? Fz 0? Because it is not in contact. We assume that this peg is sort of smoothly going into the hole. Okay. What are the artificial constraints? What are the variables you would like to control? We would like to control the z motion. We want to go slowly. Okay. So Vz is omega I. We also want to control that there is no force coming from the sides. We don't want to touch the sides, let's say. So fx and fy equal to 0. And omega z is 0, nx is 0, ny is 0. Okay. So at every stage, we can find out what are the variables which we want to control and which we cannot control. Okay. In the last stage, when it is completely inside, then what are the natural constraints? I cannot move. So all the Vx, Vy, Vz, omega x, omega y, omega z, they are all cannot be controlled. They are basically zero. Okay, it is completely inside and it is assembled. Okay, so no motion after full insertion. So what are the variables that we control when it is under full insertion? We need to make sure that it is you are not applying too much force. Okay, so there is some desired force along the x, y, and z, and a desired moment along the x, y, and z. So most of the time it will be zero or some small number, which is okay. Okay, so I am assuming that there should be no force applied after the assembly is over. Okay, so we have 4 stages and we know the natural and artificial constraint in all the 4 stages. The interesting thing is that we can find out how to switch from one stage to another stage just by monitoring the natural constraints. Okay, so there is a use for the artificial constraints. Those are the variables which we can control. We can design a controller which will control those variables. But how do we switch from stage 1 to stage 2? We monitor the natural constraints. So for example, in stage 1 to stage 2, you monitor the force along the z direction. So when it is moving in free space, Fz cannot be controlled. Fz is 0. As soon as it touches, if you are monitoring the force along the z direction, you will see some number. The sensor will see some force in the z direction. So as soon as it sees some force in the z direction, we should switch from stage 1 to stage 2. Okay, so this force should cross from some 0 to a chosen threshold value. Likewise, from stage 2 to stage 3. What is stage 2? Stage 2 is moving on the surface while in contact. But at stage 3 is when it is just on top of the hole and supposed to go in. So again, you should monitor the CZ. Okay. So you monitor the motion along the Z axis. So in stage 2, there cannot be any motion along the Z axis. Okay, but as soon as it is on top of the hole, it will start to go down. So there will be some Z motion. So this should also cross from 0 to some chosen threshold value. And finally, from stage 3 to stage 4, you monitor the force along the Z direction again. So at the end of the assembly, while assembling, we are assuming it is smoothly going into the hole, the peg. At the end, when the assembly is over, the peg goes and touches the bottom of the hole. So again, you will see some force in the Z direction. So as soon as you see some change in the value of Fz, okay, along Cz, you switch from stage 3 to stage 4. So it's a very nice way of looking at this assembly, that we can monitor the natural constraints to check when we should switch from one stage to another stage, and in each stage we control the artificial constraints. Okay, now let's look at this very important controller, which is the hybrid position and force control of robot manipulators. So till now we have seen that we need to control position along certain directions and force along some other directions. Okay, so can we have a controller which can control the desired force in the desired direction, achieve the desired force in the desired direction, and achieve the desired motion in the motion directions, which can be controlled? Okay, that is called as hybrid position force control of robots. Okay, so a little bit of introduction. Many robotic tasks require position and force control at the same time. So as in the case of grinding or assembly, I showed you certain components of force need to be controlled and certain components of position or velocity needs to be controlled. And these position and forces cannot be in the same direction, okay, because of principle of duality. The joint space schemes shown much earlier, where we had a planar 2R with constraint, is not feasible for spatial and multi-degree of freedom motion, simply because we cannot do the inverse kinematics analytically. We have a very complicated way of looking at the force in the normal direction and position in the or position control in the tangent direction in terms of the joint variables. The Cartesian position and force control algorithm can be very easily combined. I will show you. So I showed you that you have a single mass applying a force to the environment. So that is the force control part. You copy that 6 times and get it for the end effector. And likewise, I showed you how to obtain the Cartesian position control using fx, mx, cx, and so on. Okay, we write the equations of motion in terms of Cartesian end effector coordinates. Okay, we can choose the position and force control variable using a tasks planner. Okay, as shown in the examples. So using this idea of which variables can be controlled in force domain and which variables can be controlled in the position or velocity domain, we can decide. Okay, so that is called as the task planning. And then basically what we will do is we will have a selector switch, okay, which selects the appropriate position and force variables for control. Okay, so we have 6 components of position, x, y, z, and orientation, and 6 components of force and moment, fx, fy, fz, nx, ny, and z. We have a switch which will send, let's say, x from the position part, but not fx from the force part. Okay, similar. So it will be 1 from the position control part and 0 from the force control part. So it does not violate the principle of duality. Okay, so that is exactly what is shown in this figure. So we have a robot. The input to the robot is always the torque. Okay, and we measure Q and Q dot. Now using Q, okay, we can find the Jacobian matrix and we can find X and X dot. Okay, so we can do direct kinematics and find X, and we can do Jacobian and find X dot. In this Cartesian position controller, we have X desired, X dot desired, and X double dot desired. So what is this X? This is X, Y, Z and the orientation. So it's a 6-dimensional quantity. And what is the output of the Cartesian controller? It has fx, fy, fz, nx, ny, and z. Okay, we had discussed this by using the equations of motion in the Cartesian coordinates. Okay, using position and orientation of the end effector, you can derive the equation of motion in terms of the Cartesian coordinates. Likewise, let's look at the bottom part. We are going to measure the force coming from the environment. We also measure the velocity of the end effector. Okay, this x dot and this x dot is more or less same. Okay, so you go to Jacobian and you find x dot, and the input to this force controller is the desired force which this end effector must apply to the environment. Okay, so Fe desired, and this is x dot and Fe. So remember, for one axis, I had shown you that it will be some Kp into Ke inverse at KVF into x dot plus Fe desired, and whole thing multiplied by M and Kp and so on. So I had derived this force control law for one direction, for a single mass spring which is applying a force on the environment. So the output of the force controller is also a force, Cartesian force. Force means fx, fy, fz, and moments mx, my, and z. Okay, nx, ny, and z. So now we send it through these 2 selector switches, S and S prime. S prime means it is complement of S. So as I said, if I want to control, let's say, the x coordinate, okay, Vx, then I cannot take fx from this part also. So if it is Vx here, which is 1 in the selector switch, fx will be 0. So likewise, we have some 1s and 0s in the diagonal and the complementary ones. So wherever there is a 1 in the S, there will be a 0 in the S prime. Okay. So effectively what happens? We will get some forces coming from the position controller and some forces coming from the force controller, and they are consistent with the principle of duality. And you sum them over and you get the net force, and then you post multiply it by J transpose, okay, and we'll get the torque. So this torque equals J transpose F is coming from statics. This is a very basic fundamental equation. And why do we need to do this? Because the robot itself can only apply joint torques. It cannot apply external forces and moments in the end effector. Okay, so let's go over this once more. So I have one part which is the Cartesian position controller, which gives you the desired position, orientation, and its derivatives, okay, as input. It also finds a measured position and velocity, okay, from direct kinematics and Jacobian, and then we run this through this controller and we get the Cartesian forces. Likewise, we measured the external force which the environment is applying, and we measured what is the motion of the end effector. We also have an input, what is the desired force which the robot should apply, and send it through this force controller, 6 component of the single axis force controller that we had discussed, and we get the 6 components of the force vector fx, fy, fz, and x and y and z. And then we send it through these 2 switches which selects the correct ones depending on the task, okay, and then we post multiply by J transpose and we get the torque. Okay, so as an example, so as I said, the top half implements Cartesian position control, bottom half implements force control. Okay, so the output of both controllers are Cartesian forces and moments, and hence they can be combined. The matrix X, S and S prime is our selector switches to select the position and force variables according to the principle of duality. So for example, in the stage 2 peg-in hole assembly, what was stage 2? The manipulator is now touching the peg on the surface and it is moving on the surface, okay, till it goes into the hole. So while it is moving on the surface, we would like to control Vx and Vy, okay. So S, this is X, Vx, Vy, Vz, then omega X, omega Y, omega Z. Okay, so these are the force components coming from Vx, Vy, Vz, omega X, omega Y, omega Z. So we would like to control Vx and Vy and also Z. The S part, we are trying to make sure that the force in the Z direction is controlled. So this is Fx, Fy, Fz, and this is Nx, Ny, and Z. So we make sure that you are applying a contact force, and likewise Nx and Ny are controlled. Okay, so the controller sends through the force coming from Vx and Vy and omega Z, and the force through Fz and Nx and Ny. So together these 2 selector switches will now give all the 6 components of force and velocity, okay, so 6 components of force which can be controlled, and these 6 components come from suitable Vx, Vy, Vz, omega X, omega Y, omega Z, and the force along XYZ directions and moment along XYZ directions. Okay, so in summary, I showed you how we can control the force exerted by mass in one direction. Okay, so if you have a desired force which this mass needs to exert on the environment, we can design a control scheme which will do that. Okay, we extend to model based force control of manipulator in task space. Okay, so we used fx, fy, the curly f, x, and so on. We can partition a task into artificial and natural constraints. So the variables in the artificial constraints are controlled, and by principle of duality between force, moment, and position orientation variables, we cannot control both force and position in the same direction. Okay, so quote unquote force means it could be fx, fy, fz, and nx, ny, and z moments. Likewise, position could be position and or orientation. And I gave you several examples of partitioning of tasks, grinding, turning a crank, and also peg in hole assembly. And finally, I showed you how we can control position and force in together. Okay, what is called as hybrid position force control scheme. Okay, so this uses the Cartesian control of forces. Okay, so with this we come to an end to this lecture. In the next lecture, we look at some of the advanced topics in nonlinear control of manipulators. Okay.